Hello, everyone, and welcome to Introduction to Calculus with Wolfram U. My name is Devendra Kapadia, and I work here at Wolfram Research as a kernel developer for calculus functions. But I also enjoy teaching mathematics, and it's a great pleasure to have this opportunity to talk about calculus with you. Now, today is the first lesson, so I thought we'd spend some time talking about what is calculus and trying to understand what this beautiful subject is all about. So I'll begin by defining calculus, and then we'll talk a little bit about the main problems of calculus, some history, and then I'll tell you why you might want to study the course and what the course is all about. So let's begin by answering the question, what is calculus? Well, very simply, calculus is the science of change. Now, change is all around us. So, for instance, the second hand on this clock changes its position every second. But you could have more complicated motion. So, for example, the planets in the solar system change their position at every instant as they revolve around the sun. Now, in the first case, for the motion of the second hand around a clock, you could use simple arithmetic algebra to analyze a problem, but in more difficult cases like the solar system motion, you would need better tools to analyze the motion, and one such tool is calculus. So calculus is an essential tool for deeply understanding change in a mathematical way, and hence it is the tool of choice for many scientific problems. The next question is, what are the main problems that drove the development of calculus? Well, the four main problems of calculus are, first, the problem of finding the tangent line to a curve at a point. Now, if the curve is sufficiently simple, like a circle, you can of course draw the tangent line to the curve at that point. But in more complicated cases, you would need something like calculus to solve the problem. Number two is the problem of finding the area under a curve. And once again, if let's say you have a circle, then finding the area is not very difficult, but for more complicated curves, you would need better tools. Now, from a point of view of physics, you might sometimes need to find, let's say, the velocity of a particle given either its position or acceleration. And once again, you can use calculus to solve this problem. And finally, from time to time, you might want to either maximize or minimize some quantity, and the common word for that is optimizing. So, for example, a businessman might want to maximize his profit or minimize his loss. And once again, calculus is the tool which helps us to study the process of optimization. Okay, so let's look at each of these in a bit more detail. So let's begin with the tangent to a curve. Now, to find a tangent line at a point, what we do is we draw the secant lines from nearby points. So let's say you want to find a tangent at this point over here. Then you start with a point, in this case far away, and you let the secant line change by moving the point along the curve. So let's run this animation over here, and what you'll see is that as the point moves closer to the required point, the secant becomes closer and closer to the tangent. Okay, so to summarize, as the secant gets closer to the desired point, you're going to get the tangent line. Now on to the second problem for calculus, and that's the problem of finding the area or length of a curve. So here is an animation in which we're going to talk about the area of a regular polygon when the number of sides goes from 3 to 50. So let's begin with the case of n equal to 3, where you have a triangle, and then as you increase the number of sides, you'll see what happens to the perimeter and the area. So let's run the animation. You see that as the number of sides increases, the polygon approaches the circumscribed circle. And of course, in this case, you know that when you have an infinite number of sides, then you get the area of the full circle, which is just pi if the radius is 1. Okay, on to the third problem for calculus, and that is what's called the velocity problem. So here you have a particle that's moving along a knotted curve, and at each stage you have the velocity and the acceleration. So you have the tangent and the normal, as we call it, and the problem might be to compute the velocity and acceleration at any time in a very accurate way. And once again, you can use calculus for this. And finally, on to the problem of optimization. So let's say a farmer has 500 feet of fencing available, and the farmer wants to fence off a rectangle with the maximum area. The question is, what should the dimensions of the rectangle be? So let's look at this interactive model over here. You see that as you change the dimensions, you get more and more area. It increases up to a certain point, and then it starts to shrink again. So it would look like the best way to optimize over here would be to choose a rectangle, which is in fact a square, 125 feet by 125 feet. But the question is, how would you have arrived at a solution without trial and error? So calculus gives you a systematic way of solving such problems. Now, of course, the ancient Greeks knew quite a lot about solving such problems, but it was only in the 17th century that mathematicians started to look a little deeper into how one could solve each of these four problems. So the French lawyer and mathematician Pierre de Fermat developed a method for drawing tangents and finding maxima and minima. The clergyman John Wallis found ways, for example, to find the value of pi over 2 and do it quite accurately. Johannes Kepler, the great astronomer, used the method of Greeks to find the volumes of wine barrels, and in fact, in doing so, he touched upon the questions of finding volumes and finding maxima and minima. So he really is one of the pioneers of calculus. And of course, at that point, geometry was still the method of choice for many problems. So Isaac Barrow in England showed how he could calculate the tangent to a curve using purely geometrical means. So Fermat, Wallis, Kepler, and Barrow were the early pioneers of calculus, along with many others. Now, you might read in books or elsewhere that Newton and Leibniz discovered calculus. So the question is, in what sense are they regarded as the pioneers and the discoverers of calculus in the true sense? So the point is that although the early mathematicians knew about calculus in one way or the other, it was only Newton and Leibniz who gave general methods for doing calculus. In fact, they put together all the earlier knowledge and found relations between the various concepts in calculus. And one question was, who discovered calculus first? Was it Newton or Leibniz? Well, Leibniz published his paper first, but then Newton had already shared his ideas on calculus with others. So in England, people said, oh, Newton discovered calculus, while elsewhere in Europe, the support was all for Leibniz. Well, today it doesn't matter a lot, and we regard Newton and Leibniz as the joint creators of calculus, for it was they who gave a unified way of looking at concepts in this subject to us, and today we talk of the Newton and Leibniz approach to calculus. Now, beyond Newton and Leibniz, people went on making improvements in calculus. So the Bernoulli brothers were very active in this area, and in fact, John Bernoulli, wrote the first differential calculus textbook. Informally, it was L'Hopital who actually published it. Maria Agnesi, lady mathematician, she was the eldest of 21 children and still found time to do calculus and write a book that covered both differential and integral calculus. But the modern foundations of calculus, what made it really nice and precise, were given by Cauchy and Weierstrass, and it is they who finally told us how to approach calculus in a very rigorous and complete manner. Now, although all these pioneers did a lot of work, things did not stop over there, and even today we have calculus being used in many, many areas. So for example, quantum mechanics, which is the study of matter at the atomic level, uses the Schrodinger equation, which is a product of calculus. If you go to the financial markets, then the Black-Scholes equation is used to find the prices of options. And the Black-Scholes equation, in fact, uses what are called partial differential equations. When Albert Einstein wanted to discover the laws of gravitation, he had to turn to calculus, something called the Ricci calculus, and his friend Marcel Grossmann taught him the details, but Albert Einstein developed his so-called general theory of relativity based on calculus. If you study economics and you want to study markets, you need calculus. If you want to study medicine, you need calculus to figure out dosing strategies. And of course, even if you go to NASA, you would find that they use calculus all the time to figure out how to design and propel their rockets. So the point is, calculus continues to be a key tool in many different areas. But you might ask, okay, that's fine. It's really useful to some people, but why is it useful to me? So why should I study calculus? Well, I already gave you the first reason. The first reason is that it has very broad applications in the real world. The other point is a more practical one, that if you study any kind of STEM degree in science or technology, then they would ask you to first master calculus before doing anything else. So it's a prerequisite which you must go through if you want to become a technical kind of person. Now, on the other hand, you can say that I'm not going to go into any of these STEM fields, I just am going to pursue my own interests. Well, that's fine, but for anyone to master calculus represents a major academic milestone for that person. And to me, that is the main reason for studying calculus. It is a major academic milestone. If at any point in your career you can say, I know calculus, that's a great feeling. And I hope you'll get it after going through this course. Okay, so a little bit about the course itself. So this course will have 40 lessons, a 40-part course. And roughly speaking, the course is based on the AP Calculus AB in this country, in the US. So the AP Calculus course is a pretty challenging high school level course, and I thought that it'd be good to get more people into studying calculus early and preparing themselves for applying it in their own careers. Now, we'll begin with standard topics like functions and limits. And having done that, we'll move on to differential calculus. And then finally, we'll go on to integral calculus. Don't worry if you don't follow these terms. They'll get familiar to you a little later on. And of course, the only way to learn calculus or mathematics is by doing. So there'll be lots of problem sessions and quizzes to help you understand calculus in a deeper and practical way. But the main point is that we will focus on understanding, and there'll be almost no formal proofs for any theorems. So the advantage of that is that we can focus on visualization, on calculations, and really get familiar with all the things which are possible with Mathematica and the Wolfram language. So I do hope you will take advantage of this course to really understand the fundamentals of calculus, how to compute things, how to draw beautiful plots, etc., using the tools that are available to us today and were not even a few decades ago. Okay, so who's this course for? Well, you might wonder, is this course really for me? Am I old enough for it? Am I the right person? Well, it doesn't matter who you are, you will enjoy this course. So you might be a beginner trying to learn calculus. You're welcome to the course. You might be a middle schooler, for example, who is ambitious and wants to learn calculus at a very early stage. That's fine, you can learn it. This course is a good place to begin. Or you might be a doctor or an engineer who has learned calculus for sure early on, but just wants to refresh their memory and learn this wonderful subject again. That's fine, you're welcome to. You'll benefit something from this course. Now, that's specialized people, but really anyone wants to understand the Wolfram language and how to apply it to calculus is going to find this course extremely beneficial. So to me, this course is designed to be for everyone, not any specific group, and we'll try and go slow and explain things very, very carefully at every stage. So it's a good point for me to mention that this course arose in an internship project with John Clark. So John Clark was with me last summer, and in fact, he was a student at some point at the California Institute of Technology. John is a remarkable person. He learned calculus when he was in 7th grade. He's a genius, and he did a great job producing the basic material for the course. But my point is that if John, at his age, having just finished college, could write the course, you can surely follow what I'm saying over here. So do not give up. Keep persevering. The rewards will be immense. So I strongly urge you to follow the course all the way through all 40 lessons, and you will have mastered calculus by the time we are done. Okay, so let's summarize what we have learned today. So as a piece of mathematics, calculus shows us what we are capable of if we really put our minds to it. Whether Newton or Leibniz or Fermat or Marie-Agnesi, these individuals took time off from their daily duties to do what interested them most, which is mathematics and calculus, and that's why we have this wonderful subject today. Even today, if you want to do any kind of science in the broadest sense, whether it's physical science or social science, you will find calculus is a very useful apparatus, which has in fact changed our whole view of the world. Now, if you're a student, you will more or less, certainly at some stage, have to do a little bit of calculus, and you should feel proud to have mastered it yourself, beginning with this course perhaps. So that's the introduction to calculus which I've given you today, and in the next lesson we'll begin formally. It's all going to be a little more serious and straightforward in some ways, because we'll talk about functions and then slowly progress into the other areas of calculus. So with that summary, I'll conclude today's lesson. It's been a pleasure to discuss this introduction with you. I hope you have enjoyment from it. Thank you very much.